Hi guys, so here we're going to talk about heat transfer, specific heat, and calorimetry. You'll need your notes, tables B and T, and you'll also need your calculator as well. So we'll talk about heat transfer, specific heat, and calorimetry. So with heat transfer, we know that heat moves from an area of high concentration to low concentration. It's kind of like what diffusion was back in bio. So in the case here of the coffee is 70 degrees Celsius, and the environment is 20 degrees Celsius. So since the coffee is hotter, the heat is actually to transfer from the coffee to the environment. And in this case, we call this exothermic, again, because it's going from the system, which is the coffee, heat's going from the system, which is the coffee, to the surroundings. So we're going to talk about specific heat, and that has a symbol of little q. And we've briefly mentioned this in the last video when we talked about heats of phase changes, or calculating the heat of phase changes. So little q is going to be the specific heat, and that's really the amount of heat gained or absorbed or lost by an object. So if the heat is being gained, that's going to be an endothermic reaction. And if heat is being lost, that's an exothermic reaction. This can be measured in several units, 4 of which are listed here. Now the first two, you'll see they're calories and calories. Well, the first one's actually capitalized. So this is like what we call our dietary calories, so this is food, essentially. The lowercase calories is what we use in physics and chemistry to actually measure the specific heat. The difference between these is that one food calorie, or one dietary calorie, is actually equal to 1,000 physics or chem calories. We also have kilocalories, and notice that this is a little c, so 1,000 calories is equal to 1 kilocalorie. So if you notice here, 1 dietary calorie is actually equal to 1 kilocalorie. And of course we can measure them in joules or kilojoules. Now this is different than the specific heat capacity. So specific heat is Q, specific heat capacity is going to be C. This is the amount of heat per mass that's needed to raise the temperature of something by 1 degree Celsius. So for water, its value is 4.18 joules per grams degrees Celsius. It's also 1.00 calories per grams degrees Celsius. Now this one is found in Table B, and you will go ahead and put this one onto Table B as well, right? Because, again, we'll make sure that we'll need to use these for our practice problems. So specific heat, again, we've used this one's labeled Table T. We've used 2 of these equations already. The Q is equal to M times the heat of fusion, and Q is equal to M, which is mass, times heat of vaporization. This time we'll focus on this one up here. So again, Q is the heat, M is the mass, the C is specific heat capacity. For water, this is listed on Table B. And delta T is change in temperature. So whenever we deal with a change in temperature, it's the final temperature minus the initial temperature. Right, so that's, of course, delta T. And make sure that you use that, too. We'll need that a lot. Right, so make sure everything is labeled. Good. And actually, while you're here, you might as well go ahead and label these 2. These values are also found in Table B for water. All right, good. Okay, so we have the question, how many kilojoules of heat are absorbed when 100 grams of water is heated from 18 degrees Celsius to 85 degrees Celsius? So let's go ahead and figure out our knowns and our unknowns. Let's see, so if we do... Let's see, 1 kilojoules of heat, so this is our Q, it's unknown kilojoules, and since we have so many different variables, different units for heat, let's make sure that we also put that kilojoules in here too, so that we, at the end of the problem, we know what we want. Let's see, it says 100 grams of water, so we know grams is a unit for mass, so we'll go ahead and write 100. Make sure that decimal point goes in there for proper sig figs. We know it's water. and we know that we're dealing with temperature, so we actually have the initial and then the final. So it's going from 18 degrees Celsius, which is the initial temperature, to 85 degrees Celsius, which is the final temperature. So if we want to do delta T, it's the final, which is 85, minus the initial, which is 18. And you can go ahead and figure that out right now. Right. So with that ends up being, 67 degrees Celsius. So we know we have Q, we have M, and we have delta T. The only thing we're missing is actually our C. So again, we know that this is for water, so we can use the specific heat for water, or specific heat capacity, for water. Now, we have to look at our final units. They want joules at the end, not calories, so let's go ahead and use the 4.18 joules per grams times degrees Celsius. So we know we're dealing with not necessarily a phase change, so not at 0 degrees Celsius or 100 degrees Celsius. We're doing a different temperature here. So we know we need Q is equal to MC delta T. And by the way, I call this MCAT because I have an M here, and then the C delta T look like the word cat. So you'll hear many of us actually call it Q because MCAT. All right, so let's go ahead and figure out what our M is. That's 100 grams. Make sure that decimal point goes in there. And keep the units too, so that way you know that you're using the proper units. This specific heat capacity is joules per grams degrees Celsius. And the delta T is 67 degrees Celsius. Let's go ahead and check to make sure we can cancel out some units and get the unit that we want at the end. So I have grams here and here. I'll cancel those out. And I have degrees Celsius here and there. So at the end, I know I want some form of joules. So I have kilojoules here, and we can convert that afterward. All right, so go ahead and put this into your calculator. All right, so when this gets typed into your calculator, you should have 28,006 joules. The final answer went in kilojoules. So we know that if we go from joules to kilojoules, we have just to divide by 1,000. So it's 28.006 kilojoules. And let's take a look at our sig figs. I like to use the knowns and unknowns. So this has, this has 3, that has 2, and that has 3. So we use 2 sig figs at the end. So this is equivalent to 28 kilojoules. Alright, good. So let's go to the next one. So in this case, when 435 joules of heat, so this time they're giving us what the heat is, the Q is, so I'll go ahead and write that down. Q is equal to 435 joules. It's added to 3.4 grams of olive oil. So this time we have our mass is equal to 3.4 grams. And notice, they're not saying water, they're saying olive oil. So we can't use the specific heat capacity for water here. It's saying that it starts at 21 degrees Celsius and the temperature increases to 85 degrees Celsius. So the 21 was what we started with, that's our T initial, and it increases to 85 degrees Celsius, so that's our T final. So when you write this out, it's 85 minus 21. So for yourselves, that should be 64 degrees Celsius. In this case, our C is our unknown. So let's go ahead and take a look at the formula. We have Q is equal to MCAT, MC delta T. We want to solve for the C, so we have to get C all by itself. So rearrange your equation. When you do that, you should see C is equal to Q over M times delta T. So let's plug in our values. We have 435 joules for Q. The M, your mass, is 3.4 grams. And your delta T is going to be 64 degrees Celsius. All right, and at the end we have joules per grams degrees Celsius, so that's actually a unit that we want for C. All right, and and get this into your calculator, you have like 1.999, etc. So let's look how many sig figs we need. Alright, so this one has 3, that has 2, and that has 2. So let's stick to 2 sig figs. So go 1, 2, divide it up there, and this 9 increases that 9, which will increase the 1. So we end up having 2.0 joules per grams times degrees Celsius. And we're in the units that we want, so that's good. Alright, so here's calorimetry. It's used to measure the heat of reactions. Remember those delta H's I talked to you guys about in Table I and how you get them? Well, this is how you get them. So an easy way to do it would be using one of these calorimeters. So this is a cross-section of a calorimeter. These are usually insulated vessels, so you might see like styrofoam with them, because styrofoam is a really good insulator. That's why some people use them for their coffee. We have a section for their thermometer to go through, and a stirring rod, or some sort of stirring area. It's completely closed off, so we have the lid and the vessel. We want to keep this as closed as possible, because you're trying to figure out how much heat is actually going to be produced by a certain reaction, so you don't want that heat to be lost. You want to be able to measure that. Most of the time we'll use it for some of these dissolving ones, or at least that's what we'll be doing in lab. We'll take KNO3, for example, and figure out what the delta H value should be for that, or the NaOH, or the NH4Cl. So that's how we use this in lab. So there are multiple steps for this. Make sure each of these get down, because this is what's super important for making sure that you have a very accurate delta H value. The first step is to record the mass of the calorimeter. Then take the mass of the water in calorimeter. So this calorimeter on the right is typically what we have. We'll remove this part of it, these electrodes, we don't need it. You'll see this little stirring part, and then this little hole is where the thermometer goes into. So this is the calorimeter that we'll take the mass of, then we'll add water to it and take the mass again. So when we subtract these two values, we should just get the mass of the water. And we take the initial temperature of the water. Of course, we're using distilled water for all of this. That initial temperature of water should be around room temp. Then I'll give you a powder, a substance. You have to take the mass of that substance. So you just, in a separate container, just figure out what the mass of that is. And then you'll pour that substance into that calorimeter that has the water in it. Stir it, put the lid on it as quickly as possible. This is when you have to be super quick. And then record the highest or the lowest temperature. So highest if it's exothermic, lowest if it's going to be endothermic. So that way you can determine what the amount of heat lost or gained was. So this is how we do these calculations. We know that the Q of the water, and I'm just using the subscripts, so that way we can kind of figure out what all of these, we have, the Q for water, and we also have the Q for, in this case, lithium hydroxide. I might give that to you guys as well. So the Q of the water is equal to the mass of the water times the C of the water times the delta T of the water, so Q is equal to MCAT. This is for the water. The second equation is that the Q of the lithium hydroxide is equal to the MCAT of lithium hydroxide. That makes sense. We get that. So in this case, we know that Q of the water is equal to the negative Q of the lithium hydroxide. So we can actually take these two equations and set them equal to one another. Since the Q's are essentially going to be the same number, this will end up being equal to the negative of that. And that's what we have for this major equation right here. So of course this is a very super important equation. So your mass of the water, that's what we took for the calorimeter. The C of the water, that's what you know specific water to be as. The delta T of the water is that initial temperature of the water, and then the final temperature of the water. Or excuse me, the final minus the initial. Over here for the lithium hydroxide, this is why I had you take the mass of the powder. You're trying to find this. This is your unknown. And you're trying to figure out what the delta T of the lithium hydroxide is. So essentially it's going to be the same thing as there. All right? But we'll use that. We'll just figure that out as we go through. Okay, darlings? So here's a quick summary. The heat transfers from a high amount of heat to a lower amount of heat. It's kind of like diffusion back in bio. Specific heat capacity is C. It's the amount of heat per mass required to raise the temperature of something by a degree Celsius. And it's measured in joules per grams degree Celsius or calories per grams degree Celsius. We have specific heat, which is Q. It's the heat absorbed or lost by something, and that's measured in joules or calories. And calorimeters, are used to measure the specific heat of a substance, an unknown substance. And we can usually use that to compare the delta H values to that as well. So hopefully this will be helpful. Remember the units for each of the variables. And remember what the variables are, what they each stand for. That's the biggest thing for this unit, or this little lesson. Have a good day, guys.